Great, it's recording now. Let's cover a review for exam 2 today. First question deals with derivatives of inverse trigonometric functions, right? Inverse trigonometric functions. So we're going to recall this. Recall that the derivative of sine inverse of x, right? The derivative of this guy, the formula, and that formula is this: 1 over square root of 1 minus x squared, right? That's the formula. Now, why I say we need that? Well, because notice when you write out your function here, clearly this is a composite function, right? Composite function. Having this guy as your outside function, I'm not paying attention to the I'm not paying attention to number 2 because it's going to be a constant that we will pull out, but I'm paying attention to this outside function and this inside function, right? 4x cubed, right? And that is why I have written this formula. Now, just for you to know, guys, the formulas for the derivatives, all the formulas that they are here, these sheets that I gave you, right? Have them ready. They are in our website. I even gave out the links. In case you need the links, let me know. But this formula I wrote is this, right? Notice how in the formula they use parentheses here for x. The reason they do that is because usually this might not be x, might be some inside function, right? Like this, in this case, 4x cubed, right? So that is why. All right, so if you take the derivative using the chain rule, after you bring out this number 2, y prime will be twice derivative of the outside function following this formula. Following this formula should be 1 over here, square root of 1 minus something square, right? Something square times the derivative of this inside function. This something is the inside function. This is because of the chain rule, right? And here, derivative of the inside function. Anybody could tell us what's the derivative of the inside function here?
12x squared.
Excellent, guys. 12x squared, right? Excellent. Because the 3 comes down, multiply the 4, 12x squared. Yeah, I'm glad that, guys, you're sharp. You know, all these things we covered in details in the lectures. So we should be okay now with taking the derivative of composite function. Now, in the end, just put everything together, right? Number 2 times number 1 is 2 times number 12, 24, x squared. And on the denominator, we write this 1 minus. This guy is squared, look, 4 squared, 16, right? 16. X cubed squared. Remember, when you square a power, you multiply the exponents. X to the 3 times 2, 6, right? And that's it. This is the answer. Therefore, you should pick this one as your answer, right? General advice, guys, for your exam number 2, right? When you choose your answer, take your time because they are very close to each other. Look how close this choice is to this choice, right? Only the exponent look is different. So make sure, right? 24, x squared, radical, 1, 1, minus, 16, x cubed, x to the 6. Then therefore, I'm picking the wrong one, right? Yeah, it should be this, right? You see, it's clear what I said, right? The warning is even for myself, right? Yeah, so look, the answer is one thing, right? Yeah, we're right there, right? And in our exam that is no multiple choice, you get the full grade. But when you choose, sometimes these things may happen. So always double check, right? Look, double check. I realized it was this, right? Not this, even though we're very close, right? Yeah, very good. Let it serve as an example, right? Yeah, but now another thing, guys, sometimes students, they work very hard, I know, and they choose the wrong answer in some cases, right? If you send me your work, whatever you did, right, and then I verify that in your work you actually did the right thing, but then when you were choosing, you did not, I can give you some credit, not the full credit perhaps, but maybe half of the credit, something, right? Something. because it's understandable, right? But be careful there. You have 4 hours, so use your 4 hours, right? Yeah, for your exam. Great, we are good there. Crystal clear. Number 2 now. This is similar to this, so I am going to skip this. Okay, so I'm already similar, but if you feel like I shouldn't skip, I should do it, let me know and I will do it, right? But it's very similar, sine inverse, right? So this should be okay. Let's go to number 3, which is tangent inverse, a different form. Tangent inverse. It shows you here again a composite function, and we gotta recall the derivative of tangent inverse, right? Derivative of tangent inverse of x with respect to x. This is 1 over 1 plus x squared, right? It's pretty simple. Yeah. It will be good if you memorize this, but if not, not a problem, because you should have it in here, right? On the sheet for the derivative, this. And remember, they use this parenthesis because often it might not be x where you have to put there, right? You might have to go to your inside function instead of x. So that is one reason they put a parenthesis there, to remind you all that. Okay, so this is the formula for the derivative of tangent inverse. So let's do it, right? Start by writing this as follows. Tangent inverse of, that of parenthesis, right? And here you write 4x plus 3. Clearly, look, tangent inverse outside function, 4x over 3 inside function, right? So now, derivative. The derivative of the outside function has to be gotten by following this, right? The outside function. 1 over 1 plus usually it's x, but here we have an inside function, so we write that inside function here, right? 4x over 3 is square, right? Times the derivative of this inside function. Anybody here could tell us what is the derivative of this inside function? Or write it on the chat.
4 over 3.
4 over 3, Adriana. Very good. Excellent. The constant part, right? Because the constant 4/3 comes out, and the derivative of inside function is 1/4. This is 4/3. 4/3. Excellent. 4 over 3, right? And let's write it nicely there. 4 over 3 there. Very good. Now, what is next? Well, the next is just to do some algebra here and simplify, right? And simplify. So simplifying this, we're going to get the following. Y prime equal. Look here, 1 over. Let's do it carefully, right? 1 plus 4x squared. 4 squared, 16, right? 16. X squared. 3 squared, 9. 9, right? 9 in the bottom. Times this guy, right? This guy, 4/3. Let's write there, 4/3. Now next, you have to work this out. Remember, 1 is the same as 1 over 1. LCD 9, so times 9 here. So this leads to the following. Y prime equal 1 over 9 times 1, 9 plus 16. 9 plus 16 x squared. All over 9 common denominator LCD, right? Times 4/3. Next. Remember, when you divide by a fraction, you multiply by the reciprocal of the fraction, right? Or consider the reciprocal of this, you know? So y prime will be, this gets flipped, right? 9 over 9 plus 16x squared times 4 over 3. Right? Now, 9 times 4, 36. 36 divided by 3, 12, right? Or 3 into 9, 3. 3 times 4, 12. Several ways to simplify this, guys. Use your algebra. 12 over 9 plus 16 x squared, right? Now, carefully look through and see the answer there is here, right? 12 on the top, 12 on the top. 16 squared plus 9 is the same as 9 plus 16 squared, right? Order of the items doesn't change the sum. So then we're good. Very good. Very good. If something's not clear, as usual, guys, just let me know or write it in the chat, okay? I will move on. All right, that was number 3. Let's go ahead with number 4 now, number 4. So we're still dealing with derivative of inverse functions. This one deals with the product of two functions, right? Product of two functions. This guy multiply by this guy, right? Two functions being multiplied, f times g. We know that the derivative of f times g, and this is something that you have to memorize, f prime g plus g prime f, right? Or if not, you can write it out somewhere. It's called product rule. So we start with a derivative of 4x squared. That derivative is derivative will be 4 out, 4 comes down, 16 x cubed, right? Times the other function g sine inverse of x plus derivative of sine inverse. But you know the derivative of sine inverse is 1 over a square root of 1 minus x squared, right? We just saw it, times the other function 4x to the 4 power. The rest, guys, is just algebra, right? We have to kind of simplify this. Look, this will be just 16 x cubed sine inverse of x plus, look, this multiplying this 4x to the 4 on the denominator is square root of 1 minus x squared, right? Look through now the choices. If you look through the choices, that will be there. It's here, right? Professor, they wrote this first, this following. It doesn't matter. Order of the addends does not change the sum, right? So this is it. Very good. All right, moving on. I got one with secant inverse. Recall the formula for derivative of secant inverse. Secant inverse is this. Let's show you now. Derivative of secant inverse is this. 1 over absolute value of x multiplying the square root of x squared minus 1. And since we don't know the sign of x, it could be plus or minus, be careful in this part, right? Yeah. So this is a formula, right? Where I got it from? From here, from the list of formulas. Derivative of cosecant, secant, right? Secant minus, no minus, plus 1 over absolute value of x square root of x squared minus 1. Great. Let's apply this, right? Notice this function is a composite function. Composite function, Professor? Yes, because notice secant inverse is the outside function. And this 2x plus 3. 2x plus 3 over 7 is the inside function, right? Inside function. Now we're going to take the derivative using the chain rule. Using the chain rule, the derivative of this function will be derivative of outside function using this formula should be 1 over the absolute value of 2x, the absolute value of 2x, twice x plus 3 over 7, right? Multiply by the square root of this guy, the square of this 2x plus 3 over 7, right? Plus 3 over 7 squared minus 1 times the derivative of this. Anyone here in the chat could tell us what's the derivative of this inside function, 2x plus 3 over 7? Maybe if I 2 over 7, right? Note. Yeah, sometimes these notes are useful. Note that if you distribute the division of 7, this is just this. And clearly the derivative there should be just 2 2 over 7, right? Derivative is 0. So 2 over 7 here, don't forget. 2 over 7. Yeah, great. Now you have to do the algebra, right? The algebra. I'm going to kind of do it the best I can, but I might have to skip some parts because we don't have room here, right? But check this out. The absolute value that the numerator, I don't know what it is. I don't know if 2x plus 3 is positive. I don't know if 2x plus 3 is negative, right? So what I'm going to do is just this. I am going to write here on the top one, on the bottom, absolute value of 2x plus 3. But when I distribute the absolute value to the denominator, the absolute value of 7, that I know, right, is 7 because 7 is positive, right? This one without absolute value. Now, times this part. This part, guys, we did it in our notes, right? Maybe I can kind of outline here. 2x plus 3 squared divided by the square of 949, right? 7 squared 49 minus 1. And here times 2 over 7. It's a lot of algebra there, but don't get freaked out about algebra, right? It's just these computations. LCD 49, so multiply by 49 top and bottom. And then you will get the following. Y prime. Let's follow here, right? Somewhere here. Y prime will be equal to what? Well, this 1 over this fraction is the reciprocal of this fraction, right? So this gets flipped. 7 over 2x plus 3. That's that. This is going to be 49 on the bottom, common denominator 2x plus 3 squared minus 1 on the top. When you take the square root of the denominator 49, a 7 will appear there, right? A number 7 will appear there. So let's write it here. So this will be a square root of 2x plus 3 squared minus 49. But on the bottom, a square root of 49, but that's a 7, right? That's a 7. And I have here 1 on the top. And here, notice 2 over 7, right? 2 over 7. These 7 will cancel or will eliminate this 7, right? What is left? 2 times 1, 2 times 7, 14 on the top. And on the bottom, you have absolute value of 2x plus 3 multiplying by the square root of 2x plus 3 squared minus 49, right? Minus 49. So much algebra, professor. Yeah, I agree, guys, but it's just the way these formulas have to be simplified, right? So then you look through number 5, and you will find it there here. Look 14, absolute value of 2x plus 3, and the radical. Keep this in exponential form, factor form. Do not expand. It will appear there like that. Great. Very good, guys. Now, with this, we have enough taking derivative of inverse trigonometric functions, right? Now, let's go over implicit differentiation. Implicit differentiation is a technique that we use to get derivatives of functions that are defined implicitly, functions that are defined by appearing as part of an equation, right? Look, this y is not isolated, so I know that I have to follow implicit differentiation. And how this works? Well, the technique is, we explain, you take derivative with respect to x of both sides of the equation, right? Yeah. This derivative of x cubed, what is that? Anybody could tell us? Derivative of x cubed? We can write it on the chat. Yeah, very good. 3x squared, right? Very good, Oscar. Very good. Adriana, 3x squared, right? Yeah. I'm always checking, guys, derivative of polynomials, something you should walk away after taking a calculus course, because it's going to serve you a lot in the future. Derivative of cotangent of y now. Anybody could tell us derivative of cotangent y? You can look at this sheet if you need it. Now this is the one for the inverse, right? It's inverse function. Now we're working with the actual function. So this one. Find it there. Cotangent is there, right? So derivative of cotangent is gonna be minus cosecant squared, right? Minus cosecant squared. So this is what we have to write here, minus cosecant squared. But be careful there, guys, because we have to write minus cosecant squared of y. But since we are taking the derivative not with respect to y, but with respect to x, we have to attach dy dx, right? We explained this in our lecture, right? You always attach this when you deal with expressions containing y. Now, the goal is to isolate this because this is what they are looking for, right? The derivative of y with respect to x. So for that, I'm going to divide both sides by this guy, which is this minus cosecant square of y. And that should be it, right? Yeah. Here they cancel. dy dx should be equal to this guy. Minus, mathematicians often place the negative sign in the middle, right? Don't be surprised. Cosecant square of y. Professor, the derivative depends on x and y. Not a problem, guys. That's intrinsic feature of doing implicit differentiation, right? Always the derivative will depend in x, y. I wouldn't say always, but most of the time, 95% of the time. Yeah, then you look through, you find it there, right? It's there. It's here. Very good. Another example of implicit differentiation. Since this is different than that, perhaps we should do it quickly. Again, technique, take derivatives in both sides of the equation, right? Of both sides of the equation. So this is the equation. So you take the derivatives of the left side with respect to x, derivative of the right side with respect to x. Derivative here will be derivative of this part minus derivative of this part, right? Let's just write this out first. Okay, so derivative of this part will be derivative with respect to x of twice x y minus derivative with respect to x of y squared, right? Y squared. And anybody could tell me what's this derivative? Derivative of the constant function 1 with respect to x. Someone wrote in the chat. Derivatives of constant functions, since they do not change, 0. Oscar, excellent. 0. This is another thing that will serve a lot when you move on your studies, right? The derivative of constant function 0 in any context. Now, I am going to apply the product rule here, right? Product rule because I have a product of two functions, f prime g plus g prime f, right? Derivative of 2x is 2 times the function g, which is this guy, right? This is f, this is g. So y plus derivative of the function y is 1, right? Derivative of the function 1 is y. But since I am dealing with a function in terms of y, I have to attach dy dx, and then times f as a function is 2x, right? And here 0. Now I have to isolate this guy, right? Isolate this guy, get this by itself. So I'm gonna move this to the other side by subtracting 2y in both sides. So I get, let me write this here up front, 2x dy dx. Just rearranging there. And this is minus 2y, right? Yeah, I think I'm missing the derivative of this guy. Yeah, the derivative
2y,
of
yeah.
2y. Yeah, very good. I'm missing that. I was checking there. Yeah, this was too quick. This here, this derivative, guys, minus this, right? That's we need there. 2y dy dx. Now we are good. We are good to go. Right? This is the derivative of this equals 0. So subtracting 2y in both sides, here is 0. But here, notice we have to factor out now this, right? This part, factor out. We have to factor out. Let's rearrange this. Okay, so dy dx factoring out that, you get in here twice x minus twice y, right? Twice x minus twice y equal negative 2y. This disappears. Now this goes divided to the other side, right? Because if you divide both sides by 2x minus 2y, this disappears here, and this is this. Now, when you write out your answer, after you simplify this number 2 that you can factor out from there, you will notice that the answer apparently is not there, right? We discussed this on our lectures, right? But I show you a trick, right? Whenever you get an answer that apparently is not here because of a negative sign, a way to get rid of that negative sign is by multiplying numerator and denominator by -1, right? By -1. This will take care of this negative sign. And you will see that after this trick, which is a very general trick that is very highly used in mathematics, right? After the trick, notice what's going to happen. -1 times negative y, y, -1 times x, negative x. Now you look back and it appears there, right? It appears there, here. Very good for number 7D. You follow that? Yeah, don't be surprised by this, right? You multiply by -1 if needed. Very good. Number 8, I would say similar, right? Because look, product rule and then another x there. So this I will leave it for you. Number 9, perhaps deserves some attention because it's a composition of secant and 7y. Let's do it. X equal secant of 7y, right? 7y. I am going to apply implicit differentiation because I noticed that the function is defined implicitly, right? Implicitly there. So derivative with respect to x of both sides of the equation. Here, this derivative is just 1, but over here, I have to take the derivative of secant of 7y. Notice this is a composite function. So we're going to apply the chain rule, right? Derivative of secant is secant times tangent, right? Secant times tangent. Secant times tangent. But since this is a composite function, here you have to keep the inside function, right? Times the derivative of the inside function. The derivative of the inside function is 7, but since we are taking the derivative with respect to x, we have to attach dy dx, right? There you go. Now, where I got this formula, derivative of secant equals secant tangent, is here, guys, in your sheet, right? Derivative of secant, in case you did not memorize it, is here, secant times tangent, right? Yeah. All right. Now, just simplify, divide both sides of this equation by this quantity so that we isolate dy dx, right? So this one, what we're going to do next. So we're going to divide this whole thing by 7 secant of 7y tangent of 7y, right? Both sides, here and here. Very good. So then that's pretty much it, because then probably we can use some trigonometric identities to simplify that, and that will be it, right? Tangent of 7y. Notice this whole thing cancels. But over here, you get that dy dx is equal to this. Now, guys, anyone could tell me here what is 1 over secant in trigonometry? 1 over secant in trigonometry. 1 over secant. think it's is it cosine, right? Cosine, and 1 over tangent is cotangent, right? These are called reciprocal identities. 1 over secant cosine. Very good. And then 1 over tangent cotangent. Very good, Sarah. Very good. Yeah, these are things that you need to remember from pre-calculus, right? This is 1 over secant is cosine, and 1 over tangent is its reciprocal cotangent. 7y. And then that's it. You have to choose the answer now, and it's here. Right? Very good. Very good. Yeah. Next, we have to deal now with still with implicit differentiation, but now they are asking you to figure out the slope of a tangent line at some point of this curve, right? Of this curve. So let's do it together. So I have the function here defined as y to the 5th power plus x cubed equal y squared plus 9x. And I'm supposed to take derivatives of both sides with respect to x, right? To get the derivative of y with respect to x, which will be the slope of the tangent line, right? The slope which they are asking. All right, so let's do that. Derivative of y to the 5th power, so 5y to the 4th power, the derivative that comes to mind. Yeah, question, any comments, Sarah?
12 instead.
Sorry, question, you're talking about question 10 or 9?
12 instead of 10.
Oh, instead of 10, can we do number 12? That's what you're saying, Sarah?
Yes, please.
Yeah, let's do 12, 10, and then let's do 12, okay? I will do 12. Don't worry, I will remember. I will write it down. Yeah, I will not skip 12. Very good. So let's see. This is this, right? Yeah, great. And then derivative plus here, plus, but don't forget, look, derivative of y to the 5th power is a function in terms of y. So you have to attach dy dt, right? Dx plus derivative of x cubed, 3x squared. I don't have to attach anything because this function is in terms of x. Over here, derivative y squared, 2y dy dx, right? I'm dealing with a function in terms of y. Plus derivative of 9x is just the usual derivative 9. Very good. Now, I show you a trick, right? A trick that you should apply, guys, because the idea is that you should work over these exercises efficiently, right? It's a long exam. Try to conserve your energy, right? Like, you know, work efficiently. What do you mean, professor? Well, I show you this technique, right? If they give you a point where you are supposed to find the slope at, directly they are telling you that they want that slope at x equals 0 and at y equal 1, right? So one thing you can do is directly here, without isolating this, which would take time, right? As you saw before, you simply substitute there your values. Y is 1 to the 4th power. This is the derivative, but this will be the slope that I'm looking for, right? And call it just, I'm going to call it m, slope m, okay? Plus 3, x is 0, the square, twice y is 1, slope again m, plus 9, right? Now solve for m, and that's it. That will be the slope that they are asking you for m. All right, look, 1 to the 4th power 1 times 5m there, plus 3 times 0 squared 0, this whole thing 0 disappears, twice m plus 9, right? Plus 9. This disappears, minus 2m, 3m equal 9, m equal 3, right? After you divide both sides. Excellent. So we got this slope, right? Yeah. Very good. So this should be A. Very good. All right. The next question, guys, is similar. So I'm gonna skip, but similar. They want also the slope, right? So follow the same idea. But 14, someone is interested, Sarah is interested in 14, so let's do 14 quickly, okay? They want the slope at this point, 2,1. So let's do it. So if we start with x to the 6 times y to the 6 equals 60, 4, constant, right? 64. And you take derivatives in both sides, right? Derivative of both sides of the equation. Derivative with respect to x here, derivative with respect to x here. What's going to happen? Here, you're going to have the multiplication of two functions, f times g, right? F times g. And you know that in order to take that the derivative of the multiplication of two functions, you must follow the product rule, right? Which is this. So let's do it. Using product rule, the derivative of x to the 6 will be 6x to the 5th, right? 6x to the 5th times the function g, which is y to the 6th, plus derivative of g. Derivative of g is 6y to the 5th, right? But I have to attach dy dx because I'm taking a derivative of an expression containing y, right? Yeah, that's just the derivative. You still need to multiply that by f, which is this, x to the 6, right? Good news, derivative of constant function 0, right? 0. Now, I need the slope, not in general, right? Not in general. At a particular value of x, at a particular value of y. So take advantage of that, guys. I said, right? If they're giving you x and y, substitute directly here. So 6 times 2 to the 5th, y to the 6, 1 to the 6th power, plus 6, y is 1, 1 to the 5th power. This, call it m, that will be your slope, right? X 2 to the 6th power. And that's it. Then you just have to solve for x, not for x, for m. Yeah, x is known too. Great. Solve for m now. Look, 1 disappears, 1 to the 1. This 6 times 2 to the 5th power is 32 times 6. Let's find out what that is. 6 times 2 raised to the 5th power. 192. 192 here. Plus 192 plus. This is 6m. But there is 2 to the 6 now, right? 2 to the 6. So let's do that, right? Let's eliminate this. Let's compute this in the calculator. 1 disappears, there is 1 when raised to the 5th power, but 6 stays there, times 2 to the 6, right? Yeah. 384, okay? 384 m equals 0, right? Very good. Next, 192, subtracting both sides, right? 384 m equal negative 192. Divide both sides by this guy, right? And that's it. Now, comment here, right? Notice the simplification of this probably is a little bit challenging because you have to start taking halves and fourths and stuff, right? But I give you this trick, right? It's gonna be 1/2 negative, right? I know that I work with numbers all the time, but if you cannot see it quickly, right? Use this guy. Go to our decimal scientific calculator and do this. Negative 192 over 384. It gives you by default a decimal representation, right? But we want this other representation, minus 48 over 70. Yeah, we did something we have to check because it's not coming
So you
out.
input the wrong number on the calculator.
Oh, in the calculator? I'm sorry.
Yes,
yeah.
sir.
Oh, okay. So
You did 284 instead of 384.
Yeah, 3, you see? 384. Now, this is very good, right? Everything was correct. And this should serve, guys, as for you to see that in mathematics, don't get a wrong idea, right? Not everything is perfect. Things like this will happen. Let's say you're taking your exam and you get the strange number. Oh my God, don't panic, right? Calm down and check what went wrong. Right? In this case, look, if 192, I put instead of 3 a 2, just check, and then the solution will come out. Minus 1/2, right? Minus 1/2, which is there. Very good, right? There you go. Yeah, now, Sarah, everything okay with this exercise?
Yeah, I see what went wrong.
Yeah, you also couldn't get it at the right time. Yeah, it's very tricky, very tricky. I agree. Yeah, but the follow up, everything, right? And then this, I knew in my mind it was 1/2, right? But if you don't see it, I'm giving you an option, right? Put it in the calculator, go from decimal representation to the other representation, and it will come out. Negative 0.5, fraction, negative 1/2, right? Use your tools, guys. You have a lot of tools at hand. Use them, right? If one way doesn't work, use another way. I can give you a lot of strategy, right? So minus 1/2. Finally, very good. Minus 1/2. Excellent. Very good, very good. All right, great. Moving on, guys. Moving on. So
number 10.
we did that. Question, Sarah? We went to what? What we say, Sarah? Again, please.
13.
Yeah, we need to go over 13, right? Yeah. 13, here, at a given point, find the equation of the tangent line as requested. The equation, right? Not just the slope, because here we're asking us for the slope, but here they're asking us for the equation of the line. So let's do it, right? Together quickly. This looks good. So x cubed equal y squared plus 12x. Start by taking the derivatives with respect to x on both sides. Okay. Derivative of this part is 4y to the third power, right? That's the derivative that comes to mind. But since we are dealing with an expression in terms of y, we must attach dy dx, right? Yeah, great. Plus derivative of this guy, 3x squared, right? 3x squared, the usual derivative of this expression in terms of y again, 2y dy dx, right? Dy dx plus derivative of 12x is just the usual derivative 12. Great. Now, they don't want this equation in general, right? They just want the equation at this point, at x equals 0 and at y equal 1, right? So let's take advantage of that, right? I gave you this nice strategy, guys, in class, right? Directly substitute there the value of y. This guy is going to give us the slope of the tangent line. Let's call it m, plus 3 times x is 0 squared, twice y is 1, times m plus 12, right? Plus 12. From here, find your m. Solve for m as we did before. This disappears, it's 0. Equal twice m plus 12. Subtract 2m in both sides, you will get twice m equal 12. Divide both sides by 2, m equals 6, right? We got our slope. But now, in addition to this slope, I have this point, 0, 1. With the slope and the point, I can find the equation of the tangent line, right? This way, using this point slope form. This is going to be my x1, this is going to be my y1. So y minus 1 equal slope 6 times x minus 0, right? Sometimes the students say, Professor, this is just the y-intercept. If you catch that, then you can use it, right? But I'm just doing in worst case scenario, right? Yeah, so.
Professor, sorry, what about the 4m? I'm sorry. The 4m equals 2m.
4m equal this part, sir. You're talking about this? Where did it go? I skipped, because we did this, sir. Look, this, right? This is 0, and this is it. Yeah, yeah, very good, very good, guys. When I'm skipping something, guys, and you don't see it, say it, right? Don't hold it back, because it's better to clarify always, right? This that's how we actually learn. Yeah, this disappears. 6x plus 1, right? 6x plus 1 is the equation of this. Yeah, see. All right, guys. So the answer for 13 should be A, right? A. Yeah, very good, very good. 6x plus 1. Great. Now let's talk about other forms, right? Yeah, we did a lot of form. Let's talk about exponential forms. Find this derivative. This deals with the formula derivative of e to the x equal itself, right? E to the x. But in this case, we are dealing with a composite function, right? Multiplied by a constant. This is a constant, will come out, don't worry about that, but focus on this function, e raised to what? I rather write within parentheses the exponent for you to notice that it's inside function, right? The inside function, 11x. So we're gonna take the derivative of this, it's itself, right? But times the derivative of the inside function is 11, right? Derivative outside function itself, derivative inside function 11. So that's it. So derivative of this function minus 55 e raised to 11x. In case you forgot, I think everybody will keep this, right? For the forever. Derivative of e to the x, e to the x, right? It's such an easy formula to remember. It's itself, right? I use this, right? To get this derivative times the derivative inside function. So very good, guys. So that's it for 14. So we are talking about this guy, right? Moving on. Yeah, and this one requires the product rule together with the result derivative of e to the x, e to the x. Let's do it quickly. Let's call this our function f. Let's call this our function g. And applying our product rule, this will be this, right? Start with the derivative of this guy. Derivative of 2x squared is 4x, right? Times e raised to minus x, the other function, right? As it is, plus the derivative of e raised to minus x. Look, start with itself times derivative of the function that appears on the exponent, right? Which is -1. Times the other function f, 2x squared. This is it. This is the derivative of this g function, right? Yes. Yeah. So then basically, just put this together, right? Then what we can do is we can say that this should be 4x e to the minus x, and here minus 2x squared e to the minus x. Factor out the greatest common factor there, which is x squared here, 2 greatest common factor 2. For x and x squared, take the one with the smallest exponent x. This part is the same, e to the minus x, so let's factor that out too. This guy into this guy is just the number 2, minus this guy into this guy is just x, right? X minus x. That's it. That is the derivative of this g function, right? Very good, guys, very good. So is this. Very good. Moving on. Let's do one more and we can take our first break for perhaps. So what about this function where they show you the quotient of two functions? This could be your f, this could be your g, right? Since f is there, I don't want to confuse anyone. Let's call it h and let's call it g. Derivative of h over g is equal to h prime g minus g prime h over g squared, right? That's the derivative using the quotient rule. So let's do it. The derivative of this function should be derivative of the numerator 7e to the x times denominator 2e to the x plus 1 minus derivative of g, derivative of this part is twice e to the x times h times 7 e to the x, right? Very good. All that divided by the square of the function on the denominator of this, right? And advice, do not expand it, keep it like that. Simplifying, guys, look, 14 e to the twice x, right? E to the x times e to the x e to the 2x. This times this plus 7 e to the x minus 14 e to the twice x. These guys cancel, and therefore the answer should be 7e to the x over this, right? Over this cancel. Great. So that is here at choice D. Right, guys? Very good. Let's do perhaps this one quickly, and then we will move on to the break time. All right, f of x equal cosine of e to the negative twice x. Notice outside function cosine, inside function e to the negative twice x, right? So when you take the derivative, since it's a composite function, you're gonna get for your derivative of the outside function, derivative of cosine is minus sine, right? Minus sine of the inside function, is this, times the derivative of this inside function. It starts with itself times the derivative of the inside function that you see on the exponents, minus 2, and that is it, right? Minus and minus plus twice up here. This multiplication is going to be equal to e raised to negative 2x followed by sine of e raised to negative 2x, right? Try to follow this, right? Simple functions first, complicated ones, write it on the right. That's kind of the agreement, right? Yeah, and look through, and you find it here is this one, right? Follow, guys? Okay, this one is similar. It's a product rule again with the subtraction. So this similar. Let's see what comes next. This is similar to this, right? Similar to this. Instead of cosine, is sine. Similar. Let's look for new forms. This one deals with the equation of the line. Yeah, let's do this and then we'll take the break. This one, they are giving you this function and they want you to figure out the equation of the line tangent to the given curve at this point, a comma f of a, right? A equals 0. All right, so start by taking the derivative because this will give you the slope. The derivative of this composite function will be itself, the derivative of the outside function, times the derivative of the inside function 7, right? This is the derivative. Let's write our derivative nicely like this, 7e raised to 7x. Now, at x equals 0, this derivative at 0 will be this, right? 7 times 0, 0. 7 times e to the 0. This e to the 0 is 1. You can check this in your calculator. 7 times 1, 7. So the derivative evaluated at 0, 7, this is the slope, right? Slope of the tangent line, 7. The point is 0, comma. They don't give me the y coordinate, but not a problem because they are giving me the function, right? E to the 7x. Using that functions, I can figure out the y coordinate by plugging the value of x equal to 0 into the function, right? This is the partner of 0, right? So m equals 7, 0, comma. This is 7 to raise times 0 is 0, e to the 0, 1. So again, right? Find the equation having a slope 7 and containing this point 0, 1. So you do y minus y1 equal m times x minus x1, right? We've done this so many times. Y minus 1 equal slope 7, x minus 0. 0 disappears there. and you end up with this, right? Mhm. Yeah, sometimes students say, but this is just the y-intercept. If you know that, you can do it quickly, right? A slope times x plus the y-intercept 1, right? It's the same. One way or the other, guys, you should get it. All right, great. So that's number 20. Is this guy? Mhm. Very good, guys, very good. Number 21 is very similar to this, right? It's a constant you take out and basically say similar. This one, similar also, right? Similar. Let's try to go over the ones that are different. So at least we got an idea of how to deal with this. 23 is different. It says find the derivative of this function y equal natural log of 8x. I'm going to use parentheses so that I can see clearly that this is the outside function and this is the inside function, right? Yeah, great. So the derivative of this function will be derivative of natural log, remember, is 1 over the inside of the log, right? 1 over this guy, 8x. But since this is an inside function, I have to multiply by the derivative of the inside function, which is 8, right? Now, what is surprising is that is 8, it gets canceled with this 8, and then you end up with 1 over x, right? I gave you even a property, right? When they say that the derivative of natural log of some number multiplying x, it's just 1 over x. Same as the derivative of natural log of x, Professor? Yes. It's properties in mathematics, right? Great. Now, this one, 24, I think is similar, I would say. We can do it quickly, right? Natural log again, rewrite it such that you see clearly what's the inside function, what's the outside function. So derivative of this function will be derivative of the outside function first, 1 over whatever is inside the log is called the argument of the log times the derivative of this inside function, which is just 1. So the derivative of this function is just 1 over x minus 7, right? Very good. 24. This one, I would say similar, but perhaps we should do it quickly so it's a little bit different. Notice outside function, this inside function 2x squared, right? So what's the derivative of that? Well, the derivative of outside function is going to be 1 over whatever is inside the log, right? This times the derivative of this, which is 4x. Putting this together, 4x on the top, 2x squared on the bottom, simplifying, look, this is just 2. 1x cancel, 1x stays, 2 over x, right? 2 over x for 25. Excellent. Right, guys? Yeah, great. This one deals with the quotient rule, right? Quotient rule. Yeah, perhaps we should do this. And then the one with the pro rule, probably we will just consider that to be similar. So this, take it as your function f, take this as your function g. We know that the derivative of f over g is equal to f prime g minus g prime f over g squared, right? So start with the derivative of the numerator, that is 1 over x. Multiply that by the other function, x to the 7, minus derivative of g, derivative of this guy, 7x to the 6 times the function f, natural log of x, all over x to the 7 is squared, right? Square. Here, just do the math, x to the 7 on the top divided by x, x to the 6, right? X to the 6 power, 1x cancels. Minus 7x to the 6 power, natural log of x. All over x to the 7 raised to the second power, 7 times 2, 14. So you have 14 here, right? All right, now just factor out x to the 6, right? 1 minus 7 natural log of x here. and simplify, right? Simplify. Look, this simplifies with this. 6x's are canceled. 14 minus 6, 8x's survive here, right, in the bottom. So algebra, guys, right? A lot of algebra. Yeah, there 1 minus 7 natural log of x on the top. Great. So then you look through the choices and the answer should be this, right? Very good. Okay, moving on, guys. Moving on, another one, but this one I think is similar. Just use the product rule here, right? Product rule, do the simplification. It's not difficult, so similar. 28, is marked here, so we should do it. Find the derivative of y with respect to x, t, or theta as appropriate. All right, basically they're asking you to figure out a derivative, right? In this case, the function is defined in terms of theta. So therefore, we have to take our derivative with respect to theta, right? This derivative should be the derivative of this guy with respect to theta. Yeah. All right, but what is that derivative, Professor? Well, notice this natural log is our outside function, right? And this guy is our inside function, or this product. Yeah, product is the inside function, right? So the derivative of the outside function will be 1 over whatever is inside the log, right? This guy, phi theta e to the minus theta, times the derivative of the inside function, the derivative of this. But this inside function is the multiplication of two functions, right? F and g. So we're gonna use the product rule. F prime g plus g prime f. And the derivative of this f is 5. Start with that. I'm gonna place a bracket here because I'm gonna multiply by this derivative, right? 5 times the other function, e to the minus theta, right? The function g plus derivative of g, derivative of this function. Notice itself first, derivative of the outside function, but the exponent is the inside function. So you multiply by derivative of negative theta minus 1 times f times 5 theta, right? 5 theta. Yeah, be careful there, guys. Bracket here, closing this up. Now, what is left is just to kind of simplify, right? Yeah, and now that I see this here, I think we were supposed to use the properties of natural log to simplify this better, right? But let's say you don't follow the properties, you just use this, it's gonna come up anyway. Yeah, let's finish this. So this into this, notice. Yeah, let's factor out e to the theta. Yeah, I see this. We should have followed the properties of logs to simplify this. It's better. Minus 5 theta. Yeah, right. I factor out this guy so that I can cancel this e to the minus theta with this e to the minus theta, right? They cancel. So what is left? This, right? So if you divide each phi theta into 5, phi cancels, 1 over theta stays, right? Plus, minus is minus here. Minus phi theta into phi theta, 1, right? 1. So 1 theta minus 1. That's it. 1 over theta minus 1. Very good. So this is this, right? Yeah. All right. This one, guys, I would say similar, but in order to do it quickly, perhaps we should follow this, right? Recall these properties from natural logs. Natural log of a over b equal natural log of a minus natural log of b, right? Sometimes it's better to use these properties because you get to simplify the function, and then when you take the derivative, it will be easier to take the derivative. You will see, look, this is the same as natural log of e to the theta minus natural log of 4 plus e to the theta, right? Hello? Yeah. But now, natural log of e to the theta, since the natural log has base e and e here, they cancel. This is just theta. This is the properties of logs, okay? Minus natural log of 4 plus theta, right? This is just the function simplified, right? This is just y. Now take the derivative. If you take the derivative, look, derivative of theta, identity function 1, minus derivative of this 1 over the argument 4 plus e to the theta, times derivative of the inside function, derivative of this 0, derivative of this e to the theta. That's right. So the derivative will be 1 minus e to the theta over 4 plus e to the theta. Do the math here. Yeah, do the math. 1 is the same as 1 over 1. LCD 4 plus e to the theta. So times 4 plus e to the theta here, times 4 plus e to the theta here. You will get y prime equal, on the top, look, 4 plus e to the theta minus e to the theta. Good news here, look, this to cancel. 4 plus e to the theta on the bottom. So this cancel. And we get the answer, right? The answer will be 4 over this, 4 over this, right? So look for that, it's here. Right? Very good, guys, very good. Moving on, now let's go over another topic. Find the derivative of y with respect to the independent variable. This one deals with figuring out the derivatives of a function whose base is not e, right? Whose base is not e. So y equal e, not e, is 5 to the e. And I gave you a formula, right? I gave you a formula, recall? I gave you this formula. The derivative of b, any base, raised to x, with respect to x, is equal to itself, b to the x, right? But since this is not e, it's b, some other base, to compensate for that, there is this factor, natural log of b. This is the formula. Write it down. It's not on the sheets, I think, right? If needed, right? Write it down. But it's very simple to apply. Look, derivative following this formula should be itself, 5 to the x, times natural log of the base, right? 5, and done. Done. We're talking about this guy, right? For 30. Excellent, guys. Yeah. Write this formula down somewhere, right? Similar this one, right? Yeah, this one you can do similar. Instead of base 5, base 10. Very good. This one, the base is not e, is not natural log. So let's do this, and the other will be similar. Log base 10 of 2x. Recall, I gave you this formula. Recall, I gave you this formula. Derivative with respect to x of log on base b, not necessarily base e, right? Base b of x is this 1 over the stuff that is in here, x, right? Just like the derivative for natural log of x, but since this is not e, is b, to compensate for that, you attach this factor, natural log of the base, right? Write this down also, this formula if needed. So let's apply, right? Then the derivative should be what? Applying this formula. Derivative of y will be 1 over twice x. And here you attach natural log of the base, which is 10. How do you know, Professor, base is 10? When the base is not written, it's understood that the base is 10, right? We know that agreement. All right, but now be careful there, guys. This is an outside function, and this is an inside function. So you are supposed to multiply that by the derivative of your inside function, derivative of 2x2, right? 2, don't forget about that. These two will cancel these two. And finally, this will be just 1 over x multiplying natural no log of 10. Very good. And it's there. Very good. Is this? Yeah, great. Moving on, guys. Moving on. This one's similar, right? Similar. Let's try to catch different forms. This one also similar, right? It's just log base 10 again. Moving on. This one we shouldn't skip. Y equal 3 raised to natural log of 4t. Okay. Remember the formula, right? The derivative with respect to x of b to the x is equal to b to the x multiplied by natural log of b, right? Let's use the formula. This derivative will be then itself first for t times natural log of 3, right? 3. But now, guys, notice this is a composite function. Outside function 3 raised to something, inside function natural log of 4t, right? So we're going to attach here the derivative of this guy. But what's the derivative of this guy? 1 over 4t times the derivative of the inside function 4, right? So that's it. So y prime here will be equal to natural log of 3. Let's pull it out. Put the constant stuff first. Then divided by what? 4t, right? Well, the 4 cancels. Just divided by t. This is this. This is this. Multiplying 3 raised to this. Right? Looking through, you can see that that is here, right? Very good. Excellent. This one, similar to the ones that we did. Let's move on. This one's similar also. Right? Moving on. New topic. 38. Yeah, we're good. So in 38, they're dealing with rate of change, right? This corresponds to a topic related to rates. They give you a volume depending on the radius of a sphere, and they say write an equation that relates the rates of change of these two variables, right? Volume and radius. For that, you take derivative of both sides of the equation with respect to time. Always with respect to time for this related rate, remember? So you will get dv dt here on the left. On the right, the derivative of this guy will be constant 4 pi over 3 times the derivative of this, right? Which is 3 r squared dr dt, right? Because we're taking the derivative with respect to t. 3 cancels with 3, and there you get your formula, right? Look through. Is 38. See, this right? This disappears. 4 pi r squared. Very good. Next, 39. It deals with.
We already did 39.
Yeah, yesterday we did. So maybe we can.
40, 41.
Sure. Yeah, I think I did it yesterday, right? Yeah, but maybe we should do it quickly, Sarah, for everybody to kind of remember this, right? Yeah, I'm trying to kind of go over each form. Yeah, let's do it quickly. Volume, we know is 4/3 pi r cubed, right? And we got the equation, the derivatives here, right? Try to write this down in case it's not given this formula, right? The formula for the volume of a sphere, right? It should help you, right? So then you quickly divide with respect to time. And then you get your dv dt equal constant 4 pi over 3 multiplied by 3 times r squared dr dt, right? Now let's substitute what we have. Let's find what we don't have. They say that this balloon is being inflated with helium at 130 pi cubic feet per minute, right? That should be equal to this. Advice, leave pi's alone, okay? And one thing I noticed here that this 3 cancels with this 3, so we don't have to write that denominator anymore. Let's be efficient. R squared. R is what? It's given here, right? 8. They want this when R is 8 feet. And this is square dr dt. The only quantity that is not known as the RDT, that's what they want you to find, right? So you gotta divide this into this. The pi's, you can cancel them, right? Dividing pi by pi both sides, right? So do this, 130. Yeah, and if you watch the video yesterday, I think Sarah brought this up, it's there too, right? So 8 square. Guys, so then get that right. 0.51 rounded to 2 decimal places, right? 0.51. 0.51 DRDT, right? In the end, feel free to attach the units feet per minute, right? Feet per minute. And it's there, right? Very good, very good. 39. Yeah, excellent. Moving on. The ladder problem. The ladder problem, guys, is such a nice problem, right? That everybody should know how to do this problem. They say a ladder is falling at some rate. It says at a constant rate of 2 feet per second. And then because of this, since the ladder is rigid, right? Doesn't change its length, which is 10 feet, right? This guy has to move to the right, right? And actually, this is what they want you to figure out. So use Y to control the vertical distance here of this point. The horizontal distance, use X to control that. And this distance never changes, 10. So at any moment, this is true, right? From the theorem of Pythagoras. But then they say they want you to figure out this speed, this rate of change, when the bottom is 8 feet from the wall, right? When this is 8, we will do it. So take derivatives in both sides with respect to time. That's the strategy, right? This derivative will be 2x dx dt. This derivative will be 2y dy dt. And this derivative, 10 squared is 100. Derivative of constant functions, 100 is 0. Great. Now substitute what you have. Find out what you don't have. X, they are saying that they want the rate of change when X is 8. So X should be 8. Then dx dt, this is something that we don't know, which is actually what they are asking, right? To find out 2 times y. Y is now given, professor. Well, if this is 8, then y at the moment when this is 8, right, will be somewhere there perhaps. Then y will be from the theorem of Pythagoras. I'm going to write it directly here, right? 10 squared minus 8 squared, right? Yeah, from the theorem of Pythagoras, right? At the moment when this is 8, this will be 10 squared minus 8 squared, square root of that, from the theorem of Pythagoras. Now, dy dx. Now, this dy dx question for you guys. They are saying that the ladder is slipping down vertically at this speed, 2 feet per second. Should we write here 2 or minus 2? Anybody?
-2.
-2. Very good. Excellent. Great. -2. And the reason is y is decreasing over time, right? At another moment, the ladder will look like this, perhaps, right? So y is decreasing over time. That's the reason, guys, why you have to put a negative rate of change for y, okay? Because it's decreasing over time. The ladder is falling this way, right? So it's decreasing. So very important here, negative 2, right? 2. Now it's time to solve, right, for this guy. And this can be done nicely, right? So you compute this guy, right? So compute that guy and solve for the x dt, right? Very good, very good. Now, if you want to compute that guy, multiply this negative, move it to the other side, divide that into 15. For the answer to this, you should get this value. This is 6, by the way, right? 100 minus 64, 36 of 6. So maybe we should do it so I don't want to confuse anyone. This is 16 dx dt plus 2 times 6, 12 times 2, 24, minus 24 there, right? Minus 24 there. Equals 0. This 24 goes to the other side, and dx dt ends up being 24 over 16, which is approximately or exactly equal to this 1.5. Right? You get this with a calculator here, 24, 16. 1.5. Very good, guys. At the end, feel free to attach the units, right? This is the lengths are being measured in feet, the distance in seconds, so feet per second. Very good. So this is this, right? 1.5. Positive because x is increasing, right, over time. Makes sense. Very good. Excellent. Moving on, guys. So this one, the kite, I think I explained this in class. Yeah, I think. Yeah, probably we should do this, right? A man is flying a kite. The kite is here. And then this kite is being carried out horizontally away from him at this speed, 10 meters per second, right? Horizontally. So at another moment, the kite might be here. But what is constant there is the height of the kite, right? They say the height of the kite is 50 all the time, 50 here, 50 here. So if you measure this distance with x, this distance with z, at any moment, what is going to be true is this: x squared plus 50 squared equals z squared, right? Z squared. Then when you take the derivatives in both sides, what you're going to get is this: derivative of this with respect to time, derivative of this with respect to time will be derivative of this with respect to time twice x dx dt, derivative is 0, derivative of this 2z dz dt, right? Dt. Now substitute what you have, find what you don't have. Twice x. What is x? This distance. They say you're supposed to find how fast the distance between the man and the kite, this distance z, right, is changing when the kite is 130 meters away from him, when this is 130 meters, right? So 130 there. Dx dt is what? Dx dt is the horizontal rate of change, right? 10. And here twice z. What is z? Well, when this guy is 130 and this is 50 always, this will be a square root of 130 squared plus 50 squared, right? Using the theorem of Pythagoras, right? Very good, very good. And then this dz dt. From there you can find this dt. The number 2's you can cancel, and this multiplication divided by this square root, right? You can do it in the calculator. So take 130 times 10 divided by the square root of 130 squared plus 50 squared, right? Yeah, and I got this 9.3. 0.041. Very good, excellent. 9.3, right, rounded. So 9.3. The z dt 9.3 meters per second, right? In the end, you attach the units. Okay, very good, guys. Great. If you want more details on this, the explanation of this problem, if you go to a lecture of related rates, there I think I include more details, right? But since we are reviewing, this should be probably enough. Great. 42, falling water. Falling water, water is falling on a surface wetting a circular area. And we explained, right, this in class, that this is the picture you have in your mind, right? Wetted area in a circular shape. There's going to be a radius and there is going to be an area, but the area of a circle in terms of the radius is given by this formula, right? If you don't know or you don't remember, write this down. Area pi r squared, right? Very well known formula. Okay, now they say, right, how fast is the radius of the wetted area expanding when the radius is 131 millimeters? Round your answer to 4 decimal places. Okay, so we take the derivative with respect to time, which is the method that we follow when we deal with related rates, right? Remember, with respect to time. So on the left side, we will have dA dt. On the right side, pi is a constant, comes out. Derivative of r squared, the usual derivative is 2r. But since we are taking the derivative with respect to time, you have to attach the r dt, right? There we have the relationship between the rates of change. Now, let's substitute what we have and let's find out what we don't have. The rate of change for the air is given, 10 square millimeters per second. 10 is expanding, so positive, right? Pi twice r. R is given also. I think they want this when r is 131 millimeters. Okay, this is the only quantity that is unknown, and actually we have to find it, right? So just divide both sides of this equation by this multiplication of pi times 2 times 131, and you should be able to find the rate of change of the radius when the radius is equal to 131. This whole thing cancels here, the RDT equal, get your calculator, compute this, right? 10 over pi times 2 times 131. 0.0121. I'm gonna round it to 4 decimal places as requested, right? So this is it, right? 0.0121. So 0.0121. In the end, feel free to attach the units millimeters per second, right? Per second. That's it. This guy, right? Very good, very good. That's 42. Moving on. Then we talk about this profit function, right? It's application to finance, right? And we said that this should be easier than some other questions because they give you the formula already, right? You don't have to figure out the relationship between the quantities given here. Profit equal 4 times the square root of x, where x is the number of units sold. So we take derivatives in both sides with respect to time, right? Derivative of this with respect to time. Derivative of this with respect to time. Here I will get derivative of the profit, big P, with respect to time. And here I will get 4, constant 4, multiplying the derivative of this guy. But the derivative of this guy, remember, we said, right? This is another formula that you should either memorize or have it written somewhere, right? You use this formula so much, right? 1 over twice the square root of x, right? That's the formula for the derivative of the square root function. All right, so we will get 4 times 1 over twice the square root of x. 2 into 4, 2, right? 2. So let's simplify a little bit. 2, 1 over the square root of x. Great. Now, don't forget that this is a derivative with respect to time, so we have to attach the x dt here. Now let's substitute what we have. Let's find out what we don't have. We have the rate of change of the profit. It said here, if the profit keeps changing at this rate, $300 per month. So $300 per month equal twice 1 over square root of, they tell you the value of X here. They say they want you to compute this rate of change when the number of units sold is 1,700, right? 1,700 here. Times the XDT. The XDT is the only quantity that is unknown, right? We're gonna find it. Now, guys, I'm gonna be just very practical here. Look, what I'm gonna do, I'm gonna take this piece, okay, as it is, and divide it into 300. I will show you now. T equal to what? I'm gonna take the calculator, look, 300 on the top, right? Then we can choose fractional form. And on the bottom, I'm gonna write this whole thing. 2 times 1 is 2 over a square root of 1,700, right? There we go. Result, 6,184. 6,184.6, rounded to the nearest whole number, 6,185, right? 6,185. Very good, guys, very good. So this is this guy, right? Yeah, in the end, again, feel free to attach units, right? Dollars per month in this case. Per month, right? So, per month. Okay, that's it, right? Very good. Moving on. Moving on. This problem, I think we did it yesterday with Sarah requested, but we can do it again quickly, right? Quickly. So you have 2 airplanes. They are approaching to the airport. Let's say the airport is here. The one airplane is coming this way. The other airplane is coming this way, right? There is a distance between the airplanes, which we can represent with the letter Z, because Y and X are reserved to control the vertical distance, the horizontal distance, right? This is the idea here. Now, at any moment, X squared plus Y squared will be equal to Z squared, right? At any moment. Now, we take the derivative with respect to time. And this will give us the relationship between the rates of change. You will see twice X here, dx dt, plus twice Y here, dy dt, equal to Z, the derivative that comes to mind, but since we're taking the derivative with respect to time, dz dt, right? This is the relationship between the rates change. Let's substitute what we have. Let's find out what we don't have. The distance X is given here. They say that the westbound plane is at 19 kilometers from the airport. That's the moment when they want you to figure out the rate of change between the distance of the airplanes, right? If you read the word problem. So this should be just 19. Derivative of X with respect to T. This rate of change for this plane, since it's getting closer and closer to the airport, should be negative, right? Negative, because this distance is decreasing over time. And what is that? It's given here 250, right? For the second airplane, right? Negative 250. Great. Plus twice the distance Y is this other distance 26, multiplied by the rate of change of Y. They say that this airplane is coming closer and closer to the airport at this rate, 168. But since the distance Y is decreasing over time, negative, right? Negative. Very good. That's that. And this is going to be equal to twice Z. What is Z? Remember, yesterday I told you when this guy is 19. And when this guy, the vertical distance is 26, no hard to see that this guy, this Z will be equal to the square root of 26 is squared plus 19 is squared, right? And we can even calculate that so we don't have to put the whole thing in there. Using your calculator, you can get this guy here this way. The square root of 26 squared plus 19 squared is 32.20, right? 32.22. Let's say 3 digits. 32.202. 32.202. So twice 32.202. And then this multiplying dz dt, right? Dz dt. And that's it. Now, I show you a quick way to get dz dt in one step, right? So we're going to compute all this in the calculator, and then this goes dividing into this. How you do that, Professor? Well, let me show you, right? Let's try to work efficiently, guys. In your scientific calculator or in our Desmos calculator, you have to do this. Times negative 250 plus 2 times 26, right? Times negative 168. The negative sign important, guys, right? Yeah, and then since I didn't use fractional form, what I can do is I can just highlight this, click a slash, and then on the denominator, I have to type twice 32.202. It comes out negative 283.15, right? I see that the answers have been rounded to the nearest whole number, so this should be rounded to negative 283, right? Negative 283, that's it. Negative 283. In the end, guys, feel free to attach the units, kilometers per hour, right? Very good. That's it. And that's this. Very good, very good. This guy. Yeah, excellent. So we got this done. Moving on. 46, let's check the time. Yeah, we can do 2 more perhaps. Moving on. Linearization. This is an important topic, linearization, because it allows us to approximate a function with a linear function, right? And I gave you this formula. If you don't have it, it's in our notes. Is this, the linearization of a function in general is equal to f evaluated at some base point that will be given, right? Or if it is not given, you have to carefully choose it, right? Is this the formula, right? Now, our base point is 3. So we're going to do the evaluation of the function at 3 plus the derivative evaluated at 3 multiplied by x minus 3, right? This will give you the linearization, this linear function that can approximate this curve locally around this input value 3. Great. So f of 3, what's f of 3? Is the evaluation at 3, right? So either use the calculator or evaluate this doing some mental mathematics, but perhaps to play safe, we can use a calculator, right? What is this? 5 times 3 is squared. Plus 5 times 3. Minus 3. What's this? 57, right? 57. You follow, guys? 57 there. Yeah, so then this is what you have to write here, 57. And now the derivative evaluated, the derivative of this function is just 10x plus 5, right? So this derivative evaluated at 3 should be 10 times 3 plus 5. 30 plus 5, 35, right? 35 times x minus 3. And this is pretty much it. I think, yeah. So simplify. That's it, right? 7 plus 35x minus 35 times 3. 15 here, 105, right? And this simplifies to 35x minus 48, right? Yeah. 57 minus 105 minus 48. Excellent. Very good. That's it. So this is what you choose right here. This guy. Very good. Another linearization here. Yeah, question, Grace, 47.
Yes.
Yeah, for the right. Yeah, great, 47. Yeah, so this thing is similar. Let's go to 47, okay? Linearization should be derivative, not derivative, the function evaluated at A plus the derivative evaluated at A multiplied by X minus A, right? In this case, our base is the number 0. Okay, so we have to do this, right? X minus 0 disappears here, yes, X. Very good. But evaluation at 0 here, notice A times 0, 0, square root of 9 is just 3, right? 3. And if it cannot be done in your mind, you can use the calculator, right? 8 times 0, 0, square root of 9, 3. Very good. Plus the derivative of this. What is the derivative of this function? A square root function has this derivative, 1 over twice a square root, right, of 8x plus 9 times the derivative of the inside function 8, right? This is the derivative of this function, right? But we want the derivative evaluated at 0. So the derivative evaluated at 0 will be twice again. 8 times 0, good news, disappears. The square root of 9 is 3 times 2, 6. 1 over 6, right? 1 over 6. So that is what comes here, 1 over 6. Multiplying just X because 0 disappears, right? So linearization, yeah, I see. We have to check here. Forgot the 8. There is an 8 there here, 8, right? 8, 2 into 8, 4, right?
Professor,
4.
your fx
Yeah,
you
4.
need to times 8.
8, yeah, this is 4, right? 2 into 8, 4. Everybody sees that? And this 8, 2 into 8 is just 4. Yeah, as you can see, guys, whenever, when you are taking your exam, right, things are not going to be perfect. If you see that your answer doesn't appear there, just check, right? I forget something. It will
Professor,
come out.
it's not 6, it's 3.
Over 3 here, 3. Yeah, because now that 2 goes away, right? Very good. So this is 3. Yeah, just be careful there. Yeah, because this 2 cancels with this 2 into 8, 4, right? And the square root of 9, just 3, 4/3. Excellent, guys. Yeah, great. Good, right? Yeah, struggle, good, because it's sign that we are learning, right? Yeah, very good. 4/3 of X plus 3. And then you look back and it should be there then. Now it should be there, it's here. That. Very good, guys, very good. So let's see if we can do one more. Yeah, we're good, I think. Yeah, and then complete the rest. Yeah, this one, for example, another linearization. Yeah, but this will be similar because it's again with the derivative of tangent, derivative of tangent secant squared. So I would say this similar. Instead, I will go over this other form, which is this. How to compute approximately,
Please,
right?
Professor, can I give more numbers?
Sure.
55
Great.
and 58.
55 and 58. Yeah, 55. Let's make sure that we don't skip this 55 and 58, right? 55, 58. Yeah, that's it. Yeah, we will go over that. Yeah, now let me show you how you approximate the square root of 81.25 using this idea of linearization. Remember, this will be equal to what? The function evaluated at some base point plus the derivative evaluated at base point times X minus A, right? But now, what is the function, Professor? What is the base point? They don't give you the function, they give you the base point. Not hard to figure it out. Look, for the function, look at this. You're dealing with square root, right? So we're gonna let f of x be the square root of x. And for the base, anybody could tell us what could be the base here. Let a be what? What do you think should be the base? Anybody?
81.
81, right? Yeah, the idea is to choose a number that is close to this number from the right or perhaps from the left. In the homework, there are some tricky questions where you have to choose a number from the left. So, but most of the time will be a number you know, that is on the in the left in this case, right? Closest to this, right? But sometimes might be on the right. Yeah, but 81, right? From here. Great. With this, just do the following, right? Function evaluated at evaluated at 81, right? So what is that? The square root of 81, right?
81 is
It will be a
equals
9. Very good. 9. Yes, a 9. Yeah, exact, right? Now the contribution of the derivative. The derivative of the square root function is this, right? Is this. But we're evaluating at 81, our base point 81, right? Now,
Yeah.
x, what is x? X is this guy. Maybe I should highlight so you can easily figure this out. It's this guy, right? The one that we're interested in. Minus base point again, 81.
81.
There you go, right? Very good. 1/2 square root of 81 is
9.
9. And this difference is just 0.25.
0.25.
There you go. That's it, right? 0.25. Very good. Very good. That's it. And then just put this in the calculator, guys, and that's it. So try to follow this format because otherwise, perhaps it's too cumbersome sometimes, right? You have to recall the linearization. Look, if you remember, just this little shortcut, I would say, just this, right? The difference is always small and easy to compute, 0.25. And I get this number, right? Now, follow instructions, guys. They say, give your answer as a decimal round to 5 decimal places. So we'll go up to 5 decimal places there, right? Because of this 8, this becomes 9. So this is 9.01389, right? Very good, very good. Now, I would say also as an extra advice, keep in mind that you are approximating this, right? And kind of ask yourself, right? Does it look good, this approximation? Yeah, the actual value should be very close to 9, right? So this looks good. Yeah, so it's here, right? In B. Very good, guys. So this guy. Rounded to 5 decimal places. Very good. Question 52. It says, the area pi equal r squared, where r is the radius in centimeters, by approximately how much does the area of the circle decrease when the radius is decreased from 2 to 1.9 centimeters? Use 3.14 for pi. Okay. So area equal pi r squared, right? Now, this question is related to differentials, right? How do I know? Because difference of radius, they're asking me for the difference on the area, right? On the area. So remember, differentials, they work like this. You do this, GA, differential of area, equal to the derivative, which is pi 2r times differential of radius, right? This is how the differentials are related. Now, substitute, right? What you have, find out what you don't have. Differential of the area is what I need to find out. Pi here is 3.14. They are asking me explicitly to use this substitution, right? Number 2, radius. What's the radius? The first one that appears here, right? The radius goes from 2 to 1.9, decreases. So this is 2. And differential of the radius. Differential of the radius, remember, you take the last radius, 1.9, minus the first, 2.0, right? It's going to be negative, okay? Yeah, now compute this in your calculator, right? So together, so 3.14 times 2 times 2. Times 1.9 minus 2.0. All right, I get negative 1.256, right? Negative 1.256, which can be rounded to negative 1.3, right? Negative 1.3. Very good. Negative 1.3. In the end, attach the units. They're dealing with area, so it's square centimeters, right? Now, this negative it's telling you that the area is decreasing, right? So they're asking you for that decrease. So the decrease will be positive, right? We explained in class that this means decrease, right? Decrease by this amount, 1.3 square centimeters. So this, right? Follow, guys? Good. This one's similar, right? Do the same thing, but with this cubic formula, should be the same. This is simple. We will go straight to this. This will be similar to this. Okay, so they say here, determine all critical points for the function. All critical points for the function. Remember, for the critical points, we have to find the derivative, which is going to be 3x squared minus 12, right? And then we have to set our derivative equal to 0, right? Equal to 0. So set f prime of x equals 0. Equal to 0. So 3x squared minus 12 will be equal to 0. Factoring out 3, I get this, right? Factoring this difference of squares, this is x minus 2 times x plus 2, right? Equals 0. And finally, from there, I set the factors contained in the variable equal to 0, right? To find my critical points. X equal 2 will be one critical point, and x equal -2, another critical point. Now, there is another source where we should look for critical points, the values of x that makes the derivative undefined. But notice this derivative is a polynomial function. Polynomial functions are so nice, they are never undefined, right? They are okay with any real values and input values. So this is it. This is all you're gonna get for critical points, right? For 55. Very good, guys. So this is this. This similar, very similar, right? So similar. Similar. This one, I would say perhaps we can do it because it's a little bit tricky, I guess. But similar too, because it's cubic, right? So maybe we should do similar and look for different forms to ensure that we're gonna finish with the, this one, someone requested this, right? How to find the critical points of this function. Again, derivative, right? Derivative first. Derivative of this outside function, cubic function, is 3 times something raised to a second power. That something is this inside function x minus 9 times derivative of the inside function, which is just 1, right? 1, derivative of x1. This is the derivative. Now we are supposed to set this derivative, right, equal to 0, right? Let me just simplify this. 3 times 1, 3. And then set the derivative equal to 0. When you set your derivative equal to 0, you're going to get this. 3 times x minus 9 is squared equals 0. Dividing both sides of this equation by 3, we get that x squared, no, x minus 9 is squared, 0, right? 0. Now, here, take the square roots, both sides. That comes with a price, plus minus here, right? But it eliminates this guy. That's the good news. So x minus 9 equal plus minus 0. Plus minus 0 is just 0, right? 0 doesn't have a sign, 0. So from here, we get one critical point, x equal 9. There is another source to look for critical points. You can ask yourself where the derivative doesn't exist, but since you are working with a derivative having a polynomial as its formula, you don't have to waste time figuring that out because there is no way for this derivative to be undefined. This is it, right? This is it. Yeah, whoever asked for number 58 now is clear. Everything okay, right?
Yes,
I think
please.
it was
Thank
Sarah. Yeah,
Yes.
very good, Sarah. Very good. Yeah, Sarah was the one. Yeah, another one that was requested here, this one, right? How to figure out the critical points here. This one is very interesting. It will show the special case. Yeah, derivative of this is 8x minus 128. Derivative of a square root of x, 1 over, remember guys, twice the square root of x, right? That's it. Now we are supposed to set this equal to 0, right? Set y prime equal to 0 to find our critical point. So 8x minus the 2 into 128, 64, right? 64 over square root of x. Yeah, I'm trying to simplify this. All right, now let's solve this, right? I'm gonna transpose this to the other side by changing its sign, right? This. Yeah. Algebra again, right? This is why you learn a lot of algebra in previous courses, right? Here is where the reason comes up, right? Yeah, algebra. This. Now I think one thing I can do is I can multiply both sides of this equation by the denominator square root of x. Yeah, so I will have here a times square root of x times x equal 64. Very tricky. Now this has exponent 1 and this guy has exponent 1/2. So what you do here is this. First, let's divide by a both sides, kind of to get this out of the way. So we'll have x raised to 1/2 plus 1, 1/2 plus 1 equal 8. This one is 1 over 1 LCD 2. So times 2 times 2, this is 3/2, right? X raised to 3/2 equal 8. And finally, raising both sides of these equations to the reciprocal of this guy, 2/3, we will get our final answer, right? Wow, Professor, a lot of algebra. I know, guys, it's the way it is, right? This a raised to 2/3 is cube root of 8 squared, or cube root of 8 squared equivalent, right? Cube root of 64 is just 4. But I explained in our lecture, right? In case you have difficulties figuring that out, guys, just take the calculator, do this, a raised to, put the fraction there, 2/3, and this will give you the 4 that I figured out here, right? Yeah, great. Now this is one critical point, right? X equal 4. However, guys, remember we said we have another source where we look for critical point. Where was that source, Professor? That source is this. It's figure out where the derivatives may not exist, right? Yeah, let's clean this up nicely. What do you mean derivative doesn't exist? Well, look at your derivative as a function, right? Which is here somewhere, here, right? And ask yourself, is it possible for this derivative to be undefined? And for that, the hint was, right? Look at the denominator, right? Sarah, for which value of x this is undefined? Anybody?
0.
0, right? It's tricky to catch it, but for x equals 0, and the hint is look always at the denominator. The derivative at 0 will be does not exist, DNE, right? DNE does not exist. So this should be included as a critical point. Critical point x equals 0, critical point x equals 4. 2 critical points, right? So therefore, we have to go here with B, right? You follow, guys? Very tricky question, right? 0 and 2 critical points. But compare, right? Most of the time, it will be enough to take the derivative set is equal to 0 to get your critical point. But in some rare cases, this appears, this happens, right? So you should know that too. Yeah, great. Now, let's move on, guys. Let's talk about 60. Let's see. They say identify critical points. This is a quadratic function, easy. And they say find the maximum and the minimum, right? This is a cubic function, more interesting. I'm gonna do this, I'm gonna claim this as similar to this, okay? So similar here. All right, so this one, cubic, how you catch the maximum value and the minimum value. Absolute minimum, absolute minimum. We gave a method, right? We said first find your critical points. Critical points can be found by taking the derivative, setting it equal to 0. We just did this, right? Critical points here after factoring, they end up being this from here, x equal 2, one critical point. From here, x equal -2, the other critical point, right? Yeah, two critical points. Now the method is this, right? You go ahead and create a table. X here, f of x here. On that table, you are going to start by using your endpoints. These are the endpoints, right? -3 and 5. So these guys will go here and here. -3, 5. And in between, the critical points that fall in between, right? 2 falls in there, right? In between. -2 is also there, right? So there. If for some reason one of them is not there, remember you shouldn't consider it, right? We saw it in the homework problem, remember yesterday. All right, then the rest is just to make evaluations here, get the output values here and compare, right? And then pick up the largest and the smallest, right? Yeah. So you go ahead in your calculator and we're gonna use a lot this formula, right? This formula x cubed minus 12x minus 4. So start with this evaluation, use parentheses. It will be useful for the future evaluations, right? So this one cube minus 12 times x, but x is -3 for the first computation, minus 4. Aha, I see I got here positive 5. Great. Now for the next evaluation, simply copy and paste this, right? Let's try to be efficient here. And substitute this -3 for the next, -2. So basically it's just 2. You got the other output, right? 12. Continue. And now evaluation at 2. Right? -20. Continue one more time. Evaluation now at 5. The last endpoint, right? 5 here. 61. Now the idea is to look at the overall of this, right? Let's write them down here and then we will compare, okay? We'll compare. So all these values here, 5 here, first output, then 12, and there was a -20, 61, right? Clearly the largest is this, right? Largest. So this should be the max, right? Maximum. And the smallest between these three, the negative one, right? So minimum. And that's it. So you gotta say that the critical points are all of them. Remember, critical points that we got were these two, but the end points are considered to be critical points also because we explained in the lecture, right, that the technically or formally speaking, at the end point, the derivative doesn't exist. So this is included for critical points together with minimum -20, maximum 61, and it's there, right? So 61, this guy. Very good, very good. Now, this one,
To clarify, Professor, you use the derivative to compute this.
To find the critical points.
Yes,
To
okay.
find the critical
But when
point,
you
yeah.
want to find the absolute, you use the original function.
Why we use the original function?
Value of the
Yeah, because
absolute.
we are trying to figure out what is the maximum output and what is the minimum output. That's why we are using the original function.
But, so we're using this, the derivative.
No, the derivative is just a tool to catch the critical points. And maybe I should written this, right? To find critical points.
No, I get that. I'm talking about this x and x. Are we using the original function?
Yeah, the original function to do the evaluations because we want to figure out what is the absolute output value and what's the minimum output value. Yeah, that's the reason.
But the original function should be x cubed 12x minus 4, correct?
Yeah, and I use it in the decimal computation.
And then when I put -3, I got like 139.
Perhaps you are not using parentheses, Sarah. This is a very common mistake. Maybe it's this. Look, use parentheses. Parentheses here, cube, right? minus 12, parenthesis minus 3. Without parentheses, it's not gonna give you the same thing. Yeah, minus 4, 5, right? You see? Follow?
Okay. Okay.
Yeah, parentheses very important, guys. Parentheses, right? Especially if you're inputting negative numbers, right? Parentheses matters. Yeah, very good. Great, excellent. So moving on. This one I would say similar, 62. So we can move to more things. Okay, similar. This one, critical point similar. Let's talk about the mean value theorem. Mean value theorem. The mean value theorem is a theorem that says that if you have a continuous function over a closed interval, the average value of the function eventually is equal to the instantaneous rate of change at some input value between these two guys, right? Yeah. So this one is a polynomial function. It's pretty straightforward. Probably we should take a look at this other function similar to this. Let me do it with this. Okay. So the mean value theorem says that the average value of the function f of b minus f of a over b minus a should be equal to f prime of c, right? For some c between a and b. This is our a. This is our b. Now, so we have to do this, right? F evaluated at 7 minus f evaluated at a, which is 4, over 7 minus 4 equal to the derivative of this function evaluated at c. But the derivative of this function, notice this is a natural logarithm, natural log of x minus 3 will be 1 over x minus 3 times 1, derivative of the inside function, just 1 over x minus 3, right? Now, this derivative evaluated at c will be this, right? 1 over c minus 3. Yeah, that's the derivative. Very good. Now, we got to compute this whole thing. And I'm going to do it. Now, look, 7, when you put it here, 7 minus 3 is what? Natural log of 4, right? Natural log of 4. Natural log of 4. Minus 4. When you substitute here, 4 minus 3, 1. Natural log of 1. On the bottom, 7 minus 4, 3. This is equal to this. Very good. So now, substituting everything there, what do we get? Well, let's check it out. This guy can be computed in the calculator I showed in the lectures, right? You do this, natural log of 4, ln4 minus ln1. Professor, ln1 is 0. I know, guys, but in case the argument is not 1, you may have to do this, right? Let's try to do it in the most general way. Divide by 3 gives you this number, right? 0.462. Let's write it down, 0.462. 0.462 equal 1 over c minus 3. Multiply both sides of this equation by this guy. Do the math, right, carefully. And you should be able to get the value of that c that they are looking for. Yeah. So let's see. Yeah, multiplying, right, both sides by this c minus 3. Here this cancels. This is 1. This is going to be this times this, 0.462 times c minus this times 3. 3 times 0.462. 1.386. 1.386. Add this guy to both sides, and that's it basically. 0.462 c equal 2.386. Divide this guy into this guy, that should give us the answer. 2.386 over 0.462, 5.16 rounded, right? 5.164, 165, I would say, right? To decimal places from 5.165. Now, guys, check that this guy is inside the interval. Is it inside this 4,7? It is, right? So checks, it's inside. So then take it as your answer for 465, this. Take the closest, right? This is the closest. Yeah, that's it. All right, moving on. This is similar. This one is similar too, right? So use just the average change or average rate of change of the function, make it equal to the derivative, you should be fine. This one, we just did one similar. Let's go over another topic. Let's talk about, yeah, this one polynomial function was so similar. Increasing, decreasing function. Yeah, this is pretty straightforward, right? They are asking you over which interval this is increasing, over which interval is decreasing. I showed you yesterday a nice technique. Look, decreasing here, increasing here. You just have to trace the graph from left to right, right? Then decreasing here, right? Decreasing here. And this point is the local mean, right? Or it could be absolute mean, depends, right? And this one, local max in general, or perhaps could be a local max, absolute max, right? That's it. So this guy, when you look through, this is the answer. Yeah, we talk about this, right? When the graph is given, it's kind of not difficult to figure out what happens there. This is the same, right? Remember, travel along the graph from left to right, increasing here, decreasing here, increasing here again. And then when there is a change on the trend, is there where the local maximum, local minimum appears. In this case, I think here appears an absolute max, right? Absolute minimum, sorry, absolute mean, and this should be an absolute max. This should be a local max. And then increasing here, decreasing here, right? Yeah. Yeah, I think we're good with this part, 71. So let me just show you that this should be this. This one I'm more interested because they don't show you the graph, right? This is a quadratic function, is easy. So just be careful here. It's the largest open interval, right? There will be maybe more than one open interval, but choose the largest, follow the instructions. Where this is increasing, decreasing. So perhaps we can take this one as a sample, right? And the other two will be similar. Okay, so number 77, let's see. How to figure out where this function is increasing, decreasing. Well, we take the derivative, right? The derivative, which is this, because it's a composite function. And then we set our derivative equal to 0, set y prime equal to 0, to figure out where the critical points are, right? Where the critical points are. After dividing by 2 both sides, we are left with this, right? X squared minus 9 times x equals 0. These factors as x minus 3 times x plus 3 times x equals 0. And setting each factor containing the variable, we will get our critical points. One critical point here, x equal minus 3, another critical point here, and x equal 3, another critical point here. Very good. Now, these critical points must be placed on the number line, right? 0 in the middle, -3, 3. Then you are supposed to use test points, right? I'm going to do this quickly. When you set the test, use a test point 1 and put it into your derivative function, which is this, right? Notice this will be positive, right? So positive here. This guy, use another test point, let's say the number 1, put it into your derivative function. Now here, negative, right? So
Negative.
Negative, excellent, excellent. Right? Then here, -1, let's say, put it here, negative, right? But this negative, with this negative,
Negative.
positive. So positive now.
Oh, positive.
Yeah, they switch, right? This here, if you use a test point -4, let's say, -4 here, -7, -4 here, another negative, positive, but because of this, negative. So then they say take the largest interval where it's increasing. The largest is this, right? The largest. So increasing, right? Where the derivative is positive, increasing where the derivative is negative, decreasing. So increasing here, but the largest interval where it's increasing is this, right? This is from 3 up to infinity. So this guy tells you that, this guy is telling you that the answer for this question 73 should be, yeah, very good, very good. A, right? A. Right? Yeah, right. Continue. Then we talk about the derivative where a function is increasing, decreasing. Yeah, similar, right? So do that. Then you should reach the point where we have to figure out, for example, here, right? Let's take this as an example. Where is increasing, where is decreasing? All the intervals, right? So again, you take your derivative, right? This is your function. Derivative is 48 minus 3z to the second power. Then you set your derivative equal to 0. This equal to 0. Factoring out, this is 16 minus z squared equals 0. Factoring this part, you get 3 times 4 minus z times 4 plus c equals 0. Setting the factors containing the variable equal to 0, you get these two critical points, right? Z equal 4, z equal -4. Now, those guys go on the number line, right? 4 negative should be here, 4 positive should be here, right? They determine sub-interval, right? And all these guys is explaining super details in the lecture, right? But I'm kind of summarizing here. Now, the sign of the derivative here, sign of the derivative will be what? If you take a test point, let's say 5, look at your derivative, it's here, right? This is your derivative. You will 5 here is going to be negative, right? This 5 positive plus 4 positive. So the whole derivative, the whole computation will be negative, right? Negative. And you can do it, right? You can test it in your derivative function. Now, this one, I choose 0 cleverly. So 0 and my derivative looks
Positive.
0, positive, excellent, right? And this is what you think will be negative, right?
Negative.
Yeah, -5, negative, right? If you put -5 here, -5 plus 5 positive is negative, the whole thing negative, so this switch. Great. So we are looking for this interval, right? This one is decreasing, increasing, decreasing. So they are asking me to figure out where this function, that's the question here, let's see. Using the sign of the derivative, find where the function is increasing and where the function is decreasing. Okay, so we just did that, right? Decreasing here, increasing here, decreasing here. So when you look at the choices for 78, you have to say this, right? Increasing from -4 to 4 here, decreasing from negative infinity, which lives here, to -4, and union symbol, right? From 4 to infinity, right? You follow, guys? That. Yeah, now I think we should talk about how to find the extreme values, right? Local maximum, local minimum, and then we will go over concavity. Again, let me pick a cubic function, which is kind of a representative for this method. How to figure out local maximum, local minimum on this cubic function? Well, start by taking the derivative as usual, right? To find the critical points. So 3x squared here minus 12 is the derivative. Set it equal to 0. Factor. Then this is this, right? Once you factor, So you will get that your critical points are going to be 2 and -2, right? -2. Yeah, these are the critical points. You set them on the number line, -2 and 2. They create these sub-intervals, right? On the number line, this is -infinity, this is infinity. And now basically you again figure out the signs of your derivative, which is this, right? In factor form, this in expanded form. And you use test points. Let's use, for example, test point 3. If you put 3 in here, this derivative, 3 squared is 9. 9 minus 5 is positive, right? So positive. If you test with test point 0 in your derivative, 0 squared disappears, this negative. Here, if you use -3, -3 squared is the same as +3. It's going to give you the same output, positive, right? Positive. Yeah, you get the signs of the derivative. Now, this tells you that more or less this function is increasing here, right? Because positive derivative increasing reaches a point where the derivative is 0, critical point. Decreasing here reaches a point here where the derivative is 0, and then increases again. More or less, this will be the shape of the graph, right? So clearly, this is telling you that this is a local max, and this is a local mean, right? Local mean. The local max will have these coordinates, -2, and the partner of -2 via the function, right? Via this function. We can compute it. Let's see that. So -2 has this y coordinate or this partner via this function, right? Cube here -12 times -2 plus 2. 18, right? 18. 18 is the partner of -2. Okay, 18 here. And the partner of this guy, 2. So what? Again, you take the function and plug into that function now 2. 2 cubed minus 12 times 2 plus 2. And you get -14, right? -14. So this one -14, and this is there, right? -2,8 and -14 partner of 2. This one, right? Very good, guys. Very good. Now this one's similar. Let's go over another topic. Let's talk about concavity. Let's make sure that we cover concavity. In the end, last lecture yesterday, I explained that concavity deals with how the curve, between quotation, curves, right? If it curves downward or if it curves upward. We explained that if the graph curves downward, this is called concave down, right? Resembles the mouth of a frown face, right? And if the curve curves upward, if the graph curves upward, this resembles the mouth of a happy face, right? So concave down here, concave up here. And then clearly, using the concavity, not hard to see that this guy will be a local max, and this guy will be a local mean. The coordinates are there, so you should be okay identifying the local maximum, local minimum, and the concavity, and identifying this as your answer, right? Great. Okay, this is similar, right? Do the same, and concave down here, concave up here, right? Similar. Let's go ahead now with the calculation or the computations using the second derivative to determine when a function is concave up, when a function is concave down. I'm going to use this one as example, okay? So let's do 88. Suppose they give you this cubic function, they ask you where this function is concave down, where this function is concave up. For that, remember we explained you are supposed to compute the second derivative. So first derivative is 4 minus 3x squared. Second derivative is minus 6x, right? Correct? Second derivative. Now, the second derivative now is set equal to 0, right? To investigate where the function is concave up, where it's concave down. But this is a very easy equation, leads to x equals 0, right? As this is a special point where the second derivative is 0, right? So you put it there, the number line, infinity minus infinity. This separates your number line into two subintervals, right? And you got to figure out the sign of the second derivative, which is this, right? Here and here. For that, I take test point 1. I put this test point into my second derivative. Notice it's very clear that the second derivative is negative here, right? Negative. And if I take as my test point -1 here, if I evaluate into my second derivative -1, clearly this is going to be -6 times -1, +6, right? Positive. So concave up here, concave up, here concave down. Concave down. Okay. Now they are asking you to identify the concavity right over the interval. So for 88, the answer should be the first one, right? Look, concave up on -infinity to 0, concave up, and concave down on 0 to infinity, right? This is what this is saying. Very good. Yeah, this one, you follow the same method. Now, let me show you how to find this inflection point, right? Inflection point. Yeah, this is similar, but there is a moment where you are supposed to, where you will be asked to find inflection points. Let's take this cubic polynomial as an example, okay? Figure out where this is concave up, concave down, and in addition to that, show inflection points, okay? All right, so here we again go ahead, since we are dealing with concavity, we go ahead and compute our second derivative, right? But for that, we need the first derivative. First derivative of this function is 6x squared plus 2. Second derivative then will be 12x, right? 12x. We set our second derivative equal to 0. Set second derivative equal to 0. And as a result, I get this, right? 12x equals 0, divided by 12 both sides, x equals 0. This is a special point where the second derivative is 0. You set that on the number line, and you will subdivide your number line into two subintervals, right? This subinterval, this subinterval. Take these points, for example, 1, evaluate your second derivative at 1, figure out what that is. Clearly, this is just 12 times 1, positive, right? So positive 12, right? Yeah. So all these subinterval positive second derivative. Now, take another convenient test point such as -1, and figure out what is this? The second derivative evaluated -1. If you look at your second derivative function, it's just this, right? -12, which is negative. So this guy negative. So this is telling me concave down here, concave down, concave up, right? Concave up. There is change of concavity. When there is change of concavity, it means that this input value 0 together with its output value that we will find out is called an inflection point, right? Inflection point. Now, if you evaluate this at 0, this is 0, this is 0, this is just 8, right? 8. So 0,8 is the inflection point. Yeah, very good, guys. So 93 should be just this guy, right? Concave up 0 to 0, infinity, concave down -infinity to 0, inflection point 0,8. Very good. Now, this was for the case of a cubic function, right? There is a case when the function has degree 4. Let's do this, okay, to finish. So they are saying the same, right? Figure out where this function is concave up, where it's concave down, and in addition to that, find the inflection point or the inflection points. There must be perhaps more than one, right? So let's see what happens. So start by taking your derivative as usual, right? 4 comes down, multiplies 1/4, that's just 1. X to the third power stays. Then here 3x squared. Derivative is 0. Second derivative, because we're dealing with concavity, remember? 3x squared minus 6x, right? And then you're supposed to set your second derivative equal to 0 to find those special points where your second derivative is 0, right? 0. 3x greatest common factor, 3x into 3x squared is just x minus 3x into 6x, 2 equals 0. Divide by 3 both sides. You're going to get that x times x minus 2 equals 0. And setting each factor containing the variable, you get one special point there, another special point. These are not formally called critical points. They are critical points of the derivative function, if you want to call the critical points. But what really matters is that you set these 2 points on the number line, right? In the middle 0, 2 will be on the right somewhere. These 2 guys will separate your number line into 1, 2, 3 sub-intervals. Using test points, we gotta figure out what are the signs of
Sorry.
second derivative. Yeah, go ahead.
The 96, you have 1/4. Oh, okay, sorry.
It's okay? When I took the derivative, you mean
Yeah,
this 1/4? Yeah, the 4 cancels the 4 here, right? Yeah, you follow that, Sarah? Yeah, so 1 here, right?
Yes.
Yeah, it just, yeah, if you want more details of these explanations, guys, a lot of details in the lecture. But right now, since we're reviewing, I'm kind of omitting some details, right? But all details are in the lecture that are recorded. Okay, so now we have to, but ask me, right, in case something's not clear. Now we have to figure out the signs of the second derivatives over these 3 intervals, right? For that, I gave you this nice technique, the use of test point, right? For example, I take the number 3 here as a test point for this subinterval. And all I gotta do is the second derivative at 3, right? And the second derivative is this function, right? This is my second derivative, this, right? If you put this in there, this is gonna be 3 squared 9. 9 times 3, 27. 27 minus 18 is a positive number, right? And you can even calculate it. Right? In the lectures, I calculate, right? But what really matters is the sign, Let's calculate it. 3 squared. And you can use the factor form or the expanded form, doesn't matter, right? They are equivalent. So feel free to use either form. Okay, so 3. 9, right? And 9 is a positive number, right? 9. Very good. Now, this is positive. Now, you go to the other side, right? And then you gotta compute, or you gotta figure out the sign of the subinterval. Let's use it as a test point 1. Let's evaluate our second derivative at 1. If you put 1 here, notice like 3 minus 6 is a negative number, right? It's a negative number. So 3 minus 3 is a negative number. Very good. Negative now. And for this part, cleverly choose test point -1. Second derivative of -1. Notice -1, you put it here in the second derivative will be 1 positive 3 minus positive 6. -1 times positive 6, right? So 7. It would be a 7. But because of this 3 times 1, 3 plus 9, 9, right? 9, positive 9, right? Positive 9. Yeah, very good, guys. Very good. Yeah, so we have the signs of our derivative. So this means this is concave up. See, I just mute you. Yeah, it's okay. Yeah, concave up here, concave down. Sorry, I don't have space there. Down, concave down, right? And concave up here, right? Concave up. Now, difference of concavity here, right? From concave up to concave down. Again, difference of concavity here at 2, right? At 0, difference of concavity, but also at 2, difference of concavity from concave down to concave up. So, therefore, the inflection points will be what? Inflection.
Question, Professor.
Go ahead, Sarah.
Positive, positive, negative. So where would the inflection point?
You say, for example, the distribution of the signs comes up like this, positive, positive, and negative, something like this. Yeah. Then this will lead to inflection point because there is change of concavity, but this one wouldn't lead to an inflection point. You follow? Right?
So,
only when there is change of concavity, you can say that you got yourself an inflection point, right?
okay.
You follow that? Yeah. It's
So
important that change of concavity.
You take it from the plus to the negative. You don't do the plus part. That means in this situation, suppose we have plus plus, then the inflection point will be 2, comma.
Yes. If that would be the distribution of signs, right? Yeah. You will have to ignore this one, right? Yeah. Yeah, right, Sarah? Right?
Thank you, Professor.
Yeah. Very good, guys, that you put yourself in different scenarios, right? Because what if, I said, right, it doesn't happen often, but sometimes there are some examples that lead to this. Yeah, very good. What happened here? Yeah, so, yeah, it will come back. Yeah. All right, so we did all this, right? Yeah, so now we do the test points, and they will, let's just finally find our inflection points. Yeah. Remember, these were the test points. Test points, right? Yeah, let's differentiate them from the others. Yeah, that's it. All right, so now, since there is change of concavity, right? Concave, concave down, concave up, the inflection points are 0 together with its partner, with the y coordinate, right? Via the function. But this y coordinate via the function is easy to catch. This is the function. Imagine you substitute x for with 0. 0 here, 0 here. This will be 12, right? 12. So 12. This is one inflection point. And there is another one, 2, comma, the partner of 2 via this function. Probably not easy to figure out using mental mathematics. So let's use our best friend, the Desmos Scientific Calculator, right? So 4 minus 2 cubed. Yeah, be careful with the exponents, right? I get 8, right? 8 is the partner of 2 via this function, right? These are the 2 inflection points, right? Where the curvature changes, right? Either from concave up to concave down or vice versa. So therefore, for 986, you should choose this. Concave up from negative infinity to 0, right here. Concave down from 0 to 2. And concave up again from 2 to infinity, right? Which lives here. Follow, guys? Yeah, very good, guys. Okay,